The topic is on the screen. The topic is eigenvalues and eigenvectors. So this thing has too many applications in math and in other sciences. Okay. Eigenvalues and eigenvectors. Now we look at the definition first. The definition is on the screen. You are given a n by n matrix. Okay. A n by n matrix determines a linear map from Rn to Rn. We mentioned before, if the domain and the codomain are the same, we call it a linear transformation. The concept of eigenvalues and eigenvectors defined only for a linear transformation. So by that we mean defined only for in the case the domain is the same as the codomain. Okay. The definition is on the screen. You look at the left hand side in here. Okay, this is the output for the input of V under the linear transformation, and the requirement is that the output of V under the linear transformation is a scalar multiple. Is a scalar multiple of the vector. Now let me try again. Okay. Now let me try again. So probably I did not say it clearly. Okay. Again, a linear map from Rn to Rn is called a linear transformation. Now we are trying to define what we mean by an eigenvector. First of all, an eigenvector has to be a non-zero vector. It cannot be zero. It cannot be the zero vector. An eigenvector has to be a non-zero vector. The condition geometrically, it means the output for the input of V is a scalar multiple of V. If V satisfies that condition, then we call V an eigenvector. And the corresponding number T0, T0, however you say that, is called the eigenvalue. Okay. It's probably too abstract, and then we use some particular questions to talk about the meaning, the geometric meaning. Okay. Now get your handout. We are going to do all the questions in part 1, question 1 at once. So probably we can. It's okay. We will concentrate on matrix A first. Okay, now you look at part 1. Part 1, question 1a. We concentrate on A first. Okay. In the question, A is a 2 by 2 matrix. A 2 by 2 matrix determines a linear map from R2 to R2. So that's why A determines a linear transformation. Okay. Now let's recall the meaning. Okay. So maybe the solution to all the questions for the matrix A first. For the matrix A. Okay. A determines a linear transformation from R2 to R2. So because A is a 2 by 2 matrix, right? A 2 by 2 matrix, so determines a linear transformation from R2 to R2. Now I'm going to specify the rule. The rule is that every vector in R2, every vector in the domain R2, okay? So now let's say xy is mapped to the output. The output is given as follows. Probably I still want to write in columns. Every vector xy is mapped to a vector in R2. It's given by A times xy. So we have seen this too many times. I'm not going to make more comments on this. Okay. On scratch paper, you compute the output for the input of xy. Okay. Now the output for the input of xy on scratch paper, you compute a times xy. A in this particular case is 1, 0, so 0, 0, negative 1. Okay. And then xy is the input of xy. Okay. And then you multiply two matrices. I believe the first component is still x. You use that row. You use the first row to multiply that column. Okay. And then the second component is negative y. So thank you. So that's negative y. So it's x, the negative y, right? That's the answer to question A for the matrix A. And then in item number B, we are trying to describe the geometric meaning of the linear transformation. To get that, you try to get the outputs for some particular vectors. Okay. So now let's say it's not part of the solution to question number B. It's my scratch paper still. Okay. So but to do question number B, you try to choose some particular vectors. So now let's say so maybe 2, 1. Maybe the vector 2, 1. 2, 1 goes to the vector. The first component is the same. The first component is 2. Okay. And then the second component is negative y. So which is negative 1. Okay. Okay. And then so maybe you can try to sketch the input and output. When the input is 2, 1, so now let's say the vector with initial point, the origin 2, 1. I believe 2, 1 is kind of here. Okay, so the terminal point has x coordinate of 2 and the y coordinate of 1, right? And then the output for the input of 2, 1, the output for the input of 2, 1 is 2, negative 1. The first component is 2. The second component is negative 1. So do you see the output is here? If I label the input using v, then the output, now let's say, is a times v, right? A times v. So now let's say v is here. And then a times v, the output for the input of v, a times v is here. Okay. For some transformations, it's okay to use more vectors to see the input. But for this particular one, so anybody want to try to tell me the geometric meaning? If v is here, then the output of v is here. It's kind of a reflection above the horizontal axis. So do you see the meaning? If the input v is here, and then the output a times v is here. Okay. So try to understand the geometric meaning, or otherwise you cannot follow the meaning of eigenvectors and eigenvalues. Okay. Again, using a particular case, I'm trying to tell you if the input is here, if the input is the vector with the first component 2, the second component of 1, and then the output is a times v, right? A times v has the first component of 2 as well. The second component is negative 1. Okay. I'm trying to summarize the geometric meaning. I'm going to write the answer to question B on the screen. Okay. For some reason, my computer is kind of slow today. I don't know. Okay, so geometrically, it's a reflection about the horizontal axis. Okay. Or you can say geometrically, it reflects every vector in R2 above the horizontal axis. Okay. That's the official answer to question B. Of course, if you want to see more, you could use more vectors. Okay. Now here's the new thing. Here's the new thing. Now try to concentrate on the new thing. Okay. Now we are going to use the geometric meaning to understand the meaning of eigenvectors and eigenvalues. Now concentrate on eigenvectors first. Okay. Concentrate on eigenvectors first. Again, the geometric meaning is for every vector in R2, for every vector in R2, the output is a reflection above the horizontal axis. Now, can anybody tell me at least one particular non-zero vector? You listen to me carefully, okay? Can anybody try to tell me at least one non-zero vector in R2 so that the output is in the same direction as the input? I'm going to repeat my question, okay? Anybody can tell me a particular vector in R2 so that the output, the reflection, is in the same direction as the input, or in the reverse direction as the input? The same direction or the reverse direction, please. That's what we mean by a scalar multiple, right? Okay. I don't know why some people come and go. Have you had any connection problem? Okay, yeah, 1, 2 or negative 1, 2. No, so these ones may not be good, okay? Okay, now let me try to tell you at least one of those, okay? At least one of those. Again, so geometrically, it means a reflection above the horizontal axis, okay? Now I'm looking for at least one vector having the condition that the output is in the same direction as the input, okay? I will tell you one particular vector. So how about we use 1, 0, okay? We use the vector with a, so can I just use I? I is the vector with the first component of 1, the second component of 0. So give me one little moment, I'll see. If people have connection problems. Okay, if I choose I, try to understand the meaning, okay? If I reflect I above the horizontal axis, then the output of I is actually the same vector as I. I will show you the meaning, okay? It means I'm trying to say if I want to get the output for the input of I, if I'm trying to get the output for the input of I, you compute A times I, you are going to get the output for the input of I. You can do it either way. You can use the geometric meaning, it's a reflection above the horizontal axis, or alternatively you can use that rule. So how about we just use that rule, okay? A times I, you compute A times, so now let's say 1, 0, you use that rule, you have x, the first component is the same as y, right? It's the same, and then the second component is negative y, so negative 0. You still have 0, okay? I'm trying to say, so that it's nothing but I, right? So this one is I. I'm trying to say, under the linear map A, if the input is I, it maps to the same vector of y, I, okay? So that's why I is a eigenvector. I is a eigenvector, okay? Again, I want to repeat, so geometrically, a eigenvector is a vector having the condition, satisfying the condition that the output of the vector is in the same direction as the vector. So in that case, you have a eigenvector, okay? Okay. So that's one of the eigenvectors. So anybody want to tell me some other eigenvectors? 1 0 works. 1 0 works. Okay. Likewise, I believe you can see if the for any if the first component is any non-zero number, and again a eigenvector has to be a non-zero vector. Okay. If the first component is any non-zero number, now let's say a0, that's a eigenvector. Okay. I will proceed to answer question C. Okay. We'll see. I'm going to tell you why a0 is a eigenvector. Okay. Eigenvector cannot be a zero vector. So by that we mean the first component cannot be zero. Okay. Is a eigenvector. So because the output is the same as the input, okay, so which is of course in the same direction as the input. Okay, you just say something like, so because the output for the input of a0 is the same thing as a0, right? And also the corresponding eigenvalue is equal to 1. I want you to recall the definition here. Okay, the definition t0 in the definition is the eigenvalue. In this particular case, the output for the input of a0 is equal to 1 times a0. I mean a0. I'm going to remove this b, a0. Okay. And the corresponding eigenvalue is equal to 1. So can I just write 1 in here to mean it's a eigenvalue. Okay. And the corresponding eigenvalue is equal to 1. Eigenvalue is a number. Eigenvector is a non-zero vector. Okay. Again, so geometrically, it's a reflection about the horizontal axis. So that's one class of eigenvectors. Actually, we can have some other more. We can have other eigenvectors. Anybody want to tell me any other eigenvectors? For a reflection above the horizontal axis, I'm looking for some other vectors having the condition that the output is in either the same direction or in the reverse direction. In addition to vectors in the form of a0, I'm looking for some other vectors. Okay. Anybody can identify other vectors satisfying the condition that the output is in the reverse direction as the given vectors if the linear transformation is a reflection? 0, 1 is good. So 0, 1 is good. Okay. 0, 1 is good. And also, okay, so 0, 1 is good. More generally, I think you can see something like 0b. So I use 0b instead. Okay. And also, the vectors in the form of 0b are eigenvectors. I still have to specify the vectors are not zero vectors. So b cannot be 0, okay? B cannot be 0, are eigenvectors. So because the output for the input of 0b, if you do a reflection about the horizontal axis, so now let's say 0b is here. If you, that's the vector 0b, right? If you do a reflection about the horizontal axis, the output it's going to be here, right? It's going to be 0, negative b, right? I'm trying to say for any vector on the vertical axis, non-zero vector, of course, they are also eigenvectors. And the corresponding eigenvalue, anybody want to tell me the corresponding eigenvalue? The corresponding eigenvalue is a times 0b is what multiple of 0b. That question mark will give you the eigenvalue. It's negative 1. It's negative 1, of course. Okay. Thank you. Cool. It's -1. So can I just write -1? That means the corresponding eigenvalue is -1. Okay. Okay. So that's kind of the complete solution to for the matrix A. Okay. Now we'll move on to matrix B. Okay. Now let's repeat this for B. I think so. This time it could be simpler. So maybe for the matrix B, B is the matrix 2, 0, 0, -2, right? For matrix B, we answer question A first. Can I use the notation B to denote the linear map? The linear transformation, I mean. Okay. B is a 2 by 2 matrix. B determines a linear map from R2 to R2 again, right? Now let's still compute that. It means each vector in R2 is mapped to a vector in R2 given by B times xy. Okay. Simple calculation. Okay. It means each vector xy is mapped to B times xy. B times xy, I think you are going to get the first component is twice the first component in the input. The second component you are going to get is -2y. You just multiply B and y, okay, as two matrices. You are going to get that. Okay. And then you could use some particular vectors to see the meaning. So how about we still use the vector 1, 2 to try to see the meaning, okay? So now let's say the vector with the first component of 1, the second component of 2 is the vector in here. That's the vector 1, 2, okay? And then the output for the input of 1, 2 is equal to, 1, 2 goes to under the linear map. It goes to, can I use 2, 1? Sorry. So I'm trying to say my drawing is not perfect. Okay. It's not right actually. The vector I was trying to draw is the vector with the first component of 2, the second component of 1. Illustration only. Okay. Now we are trying to get the output for the input of 2 and then the second component 1. You could use the rule. I think you have to use the rule in here. Okay. And the rule, the first component it will be 4, right? 2 times 2 is 4. And then the second component is 2. Okay. I'm trying to say for the particular vector with the first component of 2, the second component of 1, the output is the vector with the first component of 4 and the second component of -2, right? So -2y. Okay. Now we are trying to sketch the output for the input of 2, 1. I still want to call this 2, 1 v. Okay. And then under the linear map B in the question, it's a vector, so somewhere in here. So this is the vector with the first component of 4, I believe, right? So that's BV. BV is the output for the input of V under B, right? That's the vector with the first component of 4 and the second component of 2, of -2, right? So this time, can anybody try to summarize the geometric meaning using one particular vector? So of course, you can use some more vectors. It's kind of a reflection about the horizontal axis again, but in addition to that, you need to do one more thing. So maybe just tell me one more thing. It's a reflection about horizontal axis. In addition to that, anybody try to describe the one more thing in addition to a reflection? You probably will have seen something like that on the quiz or in class. And double the length. Okay. I will write it down. So do you see the output BV is kind of, you reflect V, you have a vector something like this. That's the reflection of V above the horizontal axis, right? In addition to that, you double the length to get the output of the input of V. Okay. I will write the wording in here. Okay. For question B. Okay. The geometric meaning. It reflects. I mean the linear transformation B. It reflects every vector in R2 above the horizontal axis, and then double the length. Okay. All right. That's B. Okay. After getting the geometric meaning, so this time, can anybody try to describe the eigenvalues and try to tell me some eigenvectors? So maybe at least one eigenvector. At least one eigenvector, please. It's a reflection above to the horizontal axis and then double the length. I'm looking at the chat. Can anybody try to tell me, summarize some? A0, A0, and 0B. All right. Okay. So now let's say, if you have a vector A0 in here, A0 in here. I mean A0. If you reflect the vector above to the horizontal axis, it's still on the axis, right? And you double the length. I believe the output is going to be 2A0. Now let's try to see. Okay. Now for question C, so now let's say the vectors in the form of A0. Of course, eigenvectors cannot be zero vector as long as one component is not equal to 0. It's not zero vector. Okay. For every A, so maybe R eigenvectors, because either way you could use the formula we found in here, or you could use the geometric meaning. Either way, okay. Either way, the output for the input of A0 under B is equal to, if you actually compute, it's okay. It's equal to what? It's equal to 2A0, I believe, right? And the 2A0 can be rewritten in the form of 2 times A0. Okay, you look at the definition again. The definition is here. Okay. Now we have found one particular vector V, A0, right? That is in the same direction as V. It's a multiple of V, scalar multiple of V, I mean. Okay. Okay. So a vector in the form of A0 is an eigenvector, and then the corresponding eigenvalue is equal to 2. The corresponding eigenvalue. That's actually one word. So that's one word. Okay. Eigenvalue is one word. The corresponding eigenvalue is equal to 2. I think you have seen what's going on. The next class of eigenvectors are in the form of 0b, and of course the component of b is not equal to 0 are also eigenvectors. A little squeezed. Okay. So because b times b0, I mean 0b, the same argument. I believe after you calculate, it's going to be negative 2 times 0b, okay? Which means under the linear map b, 0b is mapped to a vector in the reverse direction. It's also a scalar multiple of 0b, right? And the corresponding eigenvalue is equal to is negative 2 in this particular case, right? Okay. So we're done question. We have answered questions A, B, and C for the matrix B. Now we'll move on. We'll proceed to question C. Okay. For matrix C, C determines a linear transformation from R2 to R2, of course. Okay. So C determines a linear transformation from R2 to R2. And now let's try to get the output for the input of xy, okay, for any input xy. This one is mapped to C times xy, so the same as before. It means each vector xy is mapped to a vector. You compute C times xy. I believe the first component you are going to get is negative y. Is that right? You look at the matrix C. Okay, you use that row to multiply the column xy. I think it's negative y. The second component is x. So this one is simple, right? And then what we need to do now is to identify the geometric meaning. Okay, the geometric meaning. So how about we still use the particular vector? I just did the question number A. Okay, now for question B. So how about I still use the particular vector? So now let's say the input of 1, 2. I mean 2, 1. So we have been using that many times. Okay. Now let's say that's the vector of 2. I mean that's the vector 2, 1. That's the vector v. So v has the components of 2, 1. Again, I'm trying to identify the geometric meaning for the input of using some particular vectors. I'm using 2, 1. Okay. If the input is 2, 1, I'm trying to say under C, if the input is 2, 1, and then the corresponding, so that's something you do on scratch paper. Okay. And then the output you are going to get is negative 1. The first component, negative y, right? And then the second component is x, so which is 2. Now let's try to sketch the vector, the position vector with the first component of negative 1, the second component of 2, right? The first component of negative 1, the second component is 2, okay? I believe you are going to have a vector, so somewhere in here, right? That's a vector. So can I just write CV? It means the output for the input of V. V has two components of 2, 1. Okay. So probably we have seen a linear transformation so like that before. So may not be the same. Anybody want to use that particular vector to give me a description of the geometric meaning of the linear transformation? If the input is V, the output CV is here. That's 90 degrees. Okay, I think you can see that's 90 degrees. I'm trying to motivate the answer to B. So anybody? So just tell me one word. You do not have to write the full sentence. a rotation. It's a rotation around the origin counterclockwise by 90 degrees. Okay. I will tell you the answer to question B. Okay, so the answer is something like it rotates every vector in R2 counterclockwise by 90 degrees, by half pi for the people in calculus or for whatever thing. Okay, so that's C. Again, the three questions are designed to motivate the concept of eigenvalues and eigenvectors. If C is a rotation counterclockwise by 90 degrees, is it possible for C to have eigenvectors? I mean, is it possible to have a non-zero vector satisfying the condition that the output is in the same or in the reverse direction as the input? It's impossible, right? No matter what non-zero vector you choose, after rotating counterclockwise by 90 degrees, so there's no way for the output to be in the same or the reverse direction, right? So geometrically, you can see the matrix C has no eigenvectors. Okay. It's not possible for a rotation to have eigenvectors. So geometrically is that. Okay. So we're done question 1. I will let you see what's going on next. Okay. Now, in many cases, even for 2x2 matrices, it's hard to describe the geometric meaning. It's even harder for 3x3 matrices. So later on, so now let's say if I give you a 3x3 matrix, now let's look at the last one. Okay. This one determines a linear map from R3 to R3, or a linear transformation from R3 to R3. Okay. If I want you to use the geometric meaning to find eigenvectors and eigenvalues, it would be super hard. It's next to impossible. So because the geometric meaning is hard to describe. Okay. So that's why we want to have some ways to determine the eigenvectors and eigenvalues. Actually, there's a systematic way to determine that. Okay. The systematic way is summarized as follows. Okay. In many cases, we get eigenvalues first. Okay. Still, I'm trying to tell you why. Okay. It's not hard. It's not too hard to understand why. I will go over that very quickly. Okay. Very quickly. If you do not get it, it doesn't matter. Okay. It's not going to be on the final, but the proof is not hard. I want to go over that. Okay. Okay. According to the definition, T is a eigenvalue. It means the output for the input of V. You imagine you have a n by n matrix. It can be any size. Okay. N can be any number. I mean. Okay. A n by n matrix determines a linear map from Rn to Rn. You just imagine you have a linear map from Rn to Rn. Okay. And A times V is the output for the input of V. Okay. We mentioned before, the condition here is the definition of V as a eigenvalue. It means the output of V under the linear transformation is in the same or in the reverse direction as V. Okay. T is the scalar multiple. Okay. In other words, it means the output of V is a scalar multiple times V. It's kind of in the same or in the reverse direction, right? And this equation, again, t is a eigenvalue. It means there must be a non-zero vector v satisfying that equation. Simplify a little bit, you are going to have this. It's kind of, you move all the terms to the right hand side, and then you take out a v. Okay, you're going to have that. This equation is actually a homogeneous equation with n variables and n unknowns. Now I want you to recall the Cramer's rule. Under what condition the system has a unique solution? The system has a unique solution. It means the determinant of the matrix of coefficients is not 0. So can you remember that? But we want v to be a non-zero vector, so which means we want v to be, we want the system to have a non-zero solution. So that makes sense. The determinant has to be 0. Okay. Again, if you do not fully understand that, it's okay, as long as you know how to compute eigenvalues and determine eigenvectors. So that's fine. Okay. At this point, you just remember the final conclusion. The final conclusion is the determinant of ti minus a will give you an equation of t, and you solve that equation, you can get all the eigenvalues. Of course, it's a little bit too abstract at this time. I will show you the meaning using some particular questions. Again, we are trying to develop some systematic ways to get eigenvalues and eigenvectors. Okay. That's the thing. I'm trying to determine which matrix to use. So how about we start with the matrix A first? Okay. In the process, I'm going to show you the meanings of all the items in the question. Okay. So can I copy the entire? In any case, we concentrate on eigenvalue first. I don't know what I'm doing. Okay, I will do this question a little bit slower. Okay, in the process, I will show you the meaning of everything. We'll try to answer all the questions. I'm trying to say not only question A. Okay. Now the solution. But we concentrate on getting eigenvalues first. Okay. I will see if I have summarized the step procedures or not. Okay. Probably I did. It's here. Okay. The first thing we do is to calculate the matrix Ti minus A. I'm not going to copy that. I will switch screens. Okay. Should I divide the whole thing into several steps? Yeah, probably I can. Okay. Now to work on question A, the first thing we do is to compute Ti minus A. Okay. At this time, you just imagine T is a variable. Okay. Later on, we are going to have an equation of T. The solution of the equation is going to be the eigenvalue. Okay. We compute Ti minus A first. I is the standard notation for the identity matrix. If A is a 2 by 2 matrix, then I is of course a 2 by 2 identity matrix. I will do that a little slower. Okay. So we compute Ti minus A. It means we compute T I is 1 0 0 1, right? Minus a, copy a, copy a. Okay, if you copy a, you compute 2 1 0 3. Even for this a, the geometric meaning is hard to describe, so it's very hard to use the geometric meaning to identify eigenvectors. Okay, so that's why we'll do that first. Okay. That's ti minus a. For ti minus a, so maybe try to write everything using one matrix. Okay, I believe you can follow me on the next. I'm jumping a little bit. Okay, you compute ti first. Ti, you would get t. You have two t's on the main diagonal, right? That is the main diagonal, and then you minus the thing, and then the first component will become t minus 2, right? The second, so now the first component, I mean the entry at the 1 1 location. At the 1 2 location, I think you have negative 1. At 2 1 location, at 2 1 location, I believe you have 0. Okay. At 2 2 location, you have t minus 3. So let me know if you cannot follow. It's this one should be simple, right? You just compute t times I, scalar multiplication, and then you subtract two matrices. That's ti minus a. Secondly, I don't know if I have enough space, so probably I have. Secondly, the second thing we do is to compute the determinant of ti minus a. If you look at here, the second thing we do is to compute the determinant of ti minus a. Use proper notation. Okay, use proper notation, please. You replace the brackets, the round brackets, using 2 bars to mean the determinant. The determinant of ti minus a is equal to, again, use proper notations. Okay, you replace the parentheses with the 2 bars. The determinant of t minus 2, you have negative 1 here, and then you have 0 here, you have t minus 3 here, right? In general, the answer to a determinant, if all the entries are numbers, the answer should be a number. So, but here the entries are in terms of t. After computing this, you are going to get a polynomial of t. For the people who don't remember the term is polynomial, so don't worry. You just remember the answer is in terms of t. Okay. The answer in terms of t, so you have a 2 by 2 determinant. I believe all of you guys can remember how to compute that, right? So you have t minus 2 and then times t minus 3. You multiply the two entries on the main diagonal, this one times that one, and then minus 0 times x1. Okay, minus 0 times minus 1. Of course, you do not have to write that. Okay. I told you in general you have a polynomial of degree 2 if the given matrix is a 2 by 2 matrix. To get eigenvalues, you need to factor. For this one, it's already in the factored form, so you do not have to factor. So this one is t minus 2, and then times t minus 3. Okay. In general, you need to multiply them out and factor. Okay, but this one is already in the factored form, so we're good. Okay. This polynomial of degree 2 has a name. So this one is called the characteristic equation. Actually, it's in the next step. I will introduce the term in next step. Okay. calculate the determinant, and then we let the determinant be 0. We have the characteristic equation. Okay. So the characteristic equation, is the equation you just set the determinant of ti minus a, which is a polynomial of degree 2. You just set that polynomial so to be 0. Okay. So the characteristic equation is t minus 2 and then times t minus 3 equals 0. Again, eventually we want to solve the equation. If it's not in the factor form, you have to factor. In many cases, you need to recall some techniques for factoring polynomials, quadratic functions, and so on. Right? So we're going to see more cases. So the characteristic equation is that. Now the eigenvalues are coming soon. Okay, eigenvalues are the solutions to that equation. I will show you the meaning on the handout. Okay, solve the equation. The solutions are eigenvalues of the given matrix or the linear map. It's the same thing, right? Solve the equation. We get eigenvalues. Again, that's one word. Okay, eigenvalues. We get eigenvalues. Now we have two eigenvalues, right? So we can use t1 and t2 for the two eigenvalues. Maybe one eigenvalue is t1. Okay, t1 is equal to 2. Okay, and the next eigenvalue is t2. Okay, t2 is equal to 3. Okay, so we have two eigenvalues. So this question, I went over the question so pretty slowly, so because that's the first question we are dealing with eigenvalues and so on. Okay, I have decided not going to proceed to get eigenvectors and so on. I have decided to jump to the last matrix. Okay. There's a reason I'm doing that. Your final is coming soon. Actually, I have almost decided your final is going to be closed book final using Teams. We do not have too many people in this class. I could watch you on Teams, right? But anyhow, I will make more comments when I do the review class. For this matrix, we concentrate on eigenvalues again. On the final, there will be a very similar question to that. The eigenvalues and the eigenvectors questions I'm trying to say are going to be for a 3x3 matrix. 2x2 is too small, 4x4 is too large, so 3x3 is just right. Okay. For this one, we concentrate on eigenvalues first. Okay. In step A, we find eigenvalues. Okay. I'm not going to copy the question, so maybe find the eigenvalues. So I will copy the question. Why not? For the notation, I still want to call that matrix A. Okay. So that I do not have to remember I'm not using M, I'm using A. I'm not using A, I'm using M, and so on. Okay. In any case, the first thing, so like we have seen before, the first thing you do is to compute the matrix Ti minus A. Okay. Still try not to jump too fast. Okay. It's going to be invigilated for sure, open or closed. I haven't fully decided yet. Okay, now let's compute Ti minus A first. Okay, is t. So now let's say 1 1 0 1 0 0 0 1. I mean, I'm trying to write 3 by 3 identity matrix. 0 1 0 and 0 0 1. Again, the reason is so this class for even all the quizzes, I see only 3 versions. I cannot afford to, you know what I mean. Okay, now to get ti minus a, you compute ti. Okay, I think you are going to have t minus 2 and t minus 2. I'm going to write all the entries on the main diagonal first. Okay, I think you have t minus 1 here. You kind of change all the signs in the matrix A, and you add t on the main diagonal. That's how you get ti minus a. I'm telling you a little trick. Okay, it's always the same. So now let's say you have negative 1 here, you have negative 1 here, so negative 1, you get the negation of that negative 1, 0 0. That's ti minus a. Okay. If you want to jump for this one, it's possible to jump a little bit. Okay. In the second step, you can treat the first step as compute the determinant of ti minus a. It's actually the determinant of that. It's permissible to use a notation like that. Okay. And then you replace the 2 round brackets with with 2 bars. Okay. Actually, traditionally, I have never been using open book for anything. I have been teaching 30 some years already. I think more than 30 years probably. Okay, so that's the determinant of ti minus a. Okay. And then you set the determinant to be 0. You have the characteristic equation, right? But in any case, for this one, you have many ways to evaluate the determinant. The simplest way, so anybody want to tell me a row or column you can use to multiply to compute the determinant simply? I told you on the final you're going to see something worse. The third row.
Third row.
Sure, thank you. The third row. Okay, we use the third row. To use the third row, you use the number. So now let's say t minus 1, and then you get the cofactor. I believe the cofactor is negative 1 to the power of 3 plus 3. Okay, so because t minus 1 is at 3 3 location, can I just say 3 3 location? That's in row 3 and column 3. That's a 3 3 location. So you have negative 1 to the power of 6, 3 plus 3. And then you remove the third row, the third column. You are going to have a determinant, t minus 2 in here. So t minus 2 in here, right? You have negative 1 in here, so negative 1 in here, right? You are going to end up with something like, I think t minus 1, and then negative 1 to the power of 6 is equal to positive 1. You compute the 2 by 2 determinant. So do you have t minus 2 the whole thing squared? The minus 1 minus negative 1 times negative 1. Okay, I think you know what's going on. What's 3? To factor this one, you need to do a little bit more work. Okay. T minus 1 is already in the factored form. You do not have to worry too much about that. We'll we'll proceed. For the stuff inside the brackets, you look at the mouse cursor. For the stuff inside that brackets, you have to multiply out and then factor. Okay. To multiply out, you have something like I think you have t squared minus. You really should have no trouble with this. So the prerequisite is pre-calculus 12 for this course. Okay. I think you have 14 here, and then you plus 4, and then minus 1. If you forgot, for the people who are not in calculus, I will recall a formula. The formula I was using is that a minus b the whole thing squared is equal to a squared minus 2ab and then plus b squared. I was using that formula to multiply out t minus 2 the whole thing squared. Okay. Now to save a little space, I'm going to replace 4 minus 1 with 3, of course. Now you are going to end up with t minus 1 and then times factor a quadratic equation. I mean a quadratic function of t. If you forgot that, you could be in trouble. If you forgot that, review how to factor a quadratic, a quadratic function of t. But so this one is too simple. I will make a little bit more common. Okay. To factor, you are looking for two numbers. The two numbers adding to negative 4 and multiplying to 3. So you think what are the two numbers? Again, the two numbers multiplying to negative 4, and I said something wrong. The two numbers multiplying to 3 adding to negative 4. Okay. That will give you t minus 1, right? T minus 1 and then t minus 3. I'm trying to say the two question marks are negative 1 and negative 3. Negative 1 plus the negative 3, you have negative 4, right? You multiply the two numbers, you have 3. That will give you so these two numbers. Combine the repeating factors. You have t minus 1 the whole thing squared and then t minus 3. Right. I still want to repeat the term. We have a term so which is called the characteristic equation. Characteristic equation as t minus 1 the whole thing squared and then t minus 3 equals 0. You set the determinant of ti minus a to be 0. You have an equation, right? And then after that, we are ready to get eigenvalues. Eigenvalues are, of course, eigenvalues of the given matrix A. Okay, we have two eigenvalues. One solution I'm going to call that T1. T1 is equal to negative 1, right? I mean positive 1. Sorry, it's positive 1, of course. And T2, another eigenvalue, is equal to 3. So we have two eigenvalues. Okay. After getting eigenvalues, we are going to get eigenspaces. I'm going to proceed to get eigenspaces. Now keep in mind A. Now I need B. I need the question B. I need the matrix A. In part 1, we introduced the term eigenvalues and eigenvectors. Actually, eigenspaces are formed by eigenvectors. So together with one zero vector, so together with all the eigenvectors form the eigenspaces. When doing that, you just imagine we're trying to get eigenvectors. Okay. I think the eigenvalues are 1 and 3. For each eigenvalue, we need to repeat the same thing. We're trying to get eigenvectors. Okay. We'll do that for the eigenvalue of 1 first. Okay. For the eigenvalue, so maybe T1. I think T1 is the eigenvalue of 1. Okay. For the eigenvalue of 1, now we are going to get eigenvectors for the eigenvalue of 1. So later on, I'm going to tell you a formula to remember if you have a good memory. So, but I will tell you why. Okay, I still want to tell you why. It's not too hard to understand. Okay, for the eigenvalue T1. Now let's recall we are looking for eigenvectors. Eigenvectors are the vectors in R3. Eigenvectors, it has to be the vectors. They have to be non-zero vectors. Okay, I'm trying to tell you why now. Okay, I still call that matrix A. Later on, you have something to memorize, but I still want to tell you why. According to the definition, a eigenvector is a vector. I will show you the definition somewhere. We have seen the definition using part 1, right? The definition is here. Eigenvectors are the non-zero vectors satisfying an equation like that. You imagine T0 is the eigenvalue of 1 in here. Okay. Satisfying the condition that the output for the input of V is equal to T0. T0, at this time you imagine T0 is 1, but to motivate the general case, I still want to use T0. Okay, T0 and then times V. Okay. Again, to get eigenvectors, we are looking for all the vectors in R3 satisfying equation like that. Okay. Now we move all the terms. Can I say terms to the right-hand side of the equation? Here you will have T0 and then times V, then minus A times V is equal to, it's now number 0, so 0 vector. Okay, we're dealing with all the vectors. Okay, and then you take out V from the two terms, so you are going to have T0 and then times I minus A, that's the matrix, right? And then times V is equal to 0. This equation corresponds to, I'm talking about this a little bit faster, so because that's the y side. All you need is to be able to do questions. Later on, you have a formula to memorize, so that you can do questions. Okay. This equation corresponds to a homogeneous system. Remember the term? Homogeneous is a system in which all the constants are zeros. I want to repeat, this one corresponds to a homogeneous system. Okay, solve the homogeneous system, and then the solution set will form a subspace. Okay, actually, the solution set to any homogeneous system form a subspace of R3. So probably I mentioned the conclusion before, but I'm going to make more comments later. At this point, the only thing you need to remember is that, okay, is that for a particular eigenvalue. For the eigenvalue of that, now we solve should I call that matrix equation or vector equation? So can I just call it the equation? Okay, it's actually the equation. Again, you replace t0 with t1, so you know t1 value of 1 is already an eigenvalue, so there must be eigenvectors corresponding to the eigenvalue of 1. Okay, we solve the equation. So now let's say t1 minus I. So can I write the equation twice? t1 times I, and then minus a, and then times v. Okay, and times v is equal to 0 vector. Okay, so which means I minus a, t1 is 1, right? t1 is 1, which means I minus a, and then times v is equal to the 0 vector. Okay. Very shortly, I'm going to solve a system for v. Okay, to solve the system where I'm going to introduce some notations. Okay, to solve the equations, to solve the system, I'm going to that's the matrix of coefficients. I'm going to compute the matrix of coefficients, so which is I minus a. Now let's compute that first. Okay, I minus a, you compute 1 0 0 0 1 0. That's I. Okay, 0 0 1, and then minus a you have 2. You just copy a 2 1 1 1 2 1 0 0 1. 0 0 0 1. All of you guys know how to subtract, so that's matrix. Okay, so you're going to end up with the okay, I think you have 1 1 0 on the main diagonal. Negative 1 0 on the main diagonal, right? And then for all other entries, you have negative 1 here, you have negative 1 here, negative 1 0 0. Can anybody double check for me? I was just trying to compute I minus a. You have I, you have a, right? You have I minus a, right? I still want to specify v. Okay, v is a vector we're looking for. Whatever notation you want to use. So can you use you could use x by z, or you could use x1, x2, x3, the same thing. So can you use x by z instead? These are the vector consisting of all the unknowns. Okay, and then the right hand side, of course, the 0 vector is the vector with the 3 components of zeros. Now we're talking about everything in R3. Okay. Now do you see the system? We have a matrix of coefficients of that. The equation we are trying to solve, I hope I'm not jumping too much, but we have seen this too many times. Okay. So we have the equation we want to solve. It's going to be the equation. I'm not going to copy the equation. Okay. The equation we want to solve is corresponding to a system of 3 linear equations in 3 unknowns. I hope you can identify the augmented matrix. Augmented matrix is matrix of coefficients is I minus a. So you have the first row, so it is negative 1, negative 1, negative 1. The second row is also negative 1, negative 1, negative 1, and then the last row you have 0, 0, 0, right? And then the last column corresponds to the constant terms, I think you have all zeros. Again, we are trying to solve the system. In the system, the augmented matrix is that, okay? Okay, anybody want to tell me the solution to the system? How many columns? Yeah, so put the matrix into REF. Put the matrix into REF, please. I think you are going to... So that's simple, right? I think you are going to have 1, 1, 1, the first row, 1, 1, 1, 0. The second row and the third row are going to be all zeros. Okay. I want to repeat. The solution set is the eigenspace we are looking for. You have only one leading one of row 1, right? Okay, now the solution set. The general solution, I mean. The general solution. So now let's try not to jump too fast. Okay. The general solution, I believe you set y to be a parameter of R, right? And then you set z to be the parameter of S. So do you see there are 2 columns without leading ones, right? Okay. And then X is determined by y and z, so which is negative R minus S. So correct me if you see anything wrong, okay? You could write something like R and S are parameters. That's my parameter, okay? I'm a little bit squeezed. Now we are ready to get the eigenspace for the eigenvalue of 1. The notation for the eigenspace for the eigenvalue of 1 is E sub 1, okay? E sub 1, you do not have to tell me the meaning, okay? But E sub 1 is called the eigenspace for the eigenvalue of 1. You just put all the components. You just put x, y, and z in terms of R and S as components. The first component is negative R, the second component is minus S. I mean, the second component is R, the third component is S. Say something like you let R and S run through all the real numbers. Trust me, all the vectors in that set are eigenvectors. I mean, the outputs are in the same or in the reverse directions. Okay. We are not done yet, so that's only one eigenspace. We have 2 eigenvalues. We still need to repeat the same thing for the other one. Okay. So this time I'm going to run a little bit quicker. Okay. For the eigenvalue, so T2, I think T2 value is 3, right? We solve an equation. The equation you have to memorize is T2 value of 3. Okay. The equation is 3i minus a, right? And then times b equals the 0 vector. It's very similar to the question we just did. Okay. Now we just compute 3i minus a. 3i minus a. I think you have negative 1 here. 3i minus a. I think you have 1, 1, 1, 1, 2 on the Venn diagonal. Is that right? 3i minus a. And all other numbers, you have negative 1 here, negative 1 here, 0, 0, 2. Okay. That's 3i minus a. Okay. And the same as before, you could use xyz to denote v. So you have xyz for v. Okay. And then the 0 vector the zero vector is something like 0, 0, 0, right? Okay. The final schedule has been posted on the website. You check the website. Okay, so that's the setup for the system. Now, to solve the system, you put the matrix into REF, augmented matrix 1, negative 1, negative 1, negative 1, 1, negative 1, 0, 0, 2. Sorry. I mean, that's my bar, so that's a bar. To the right of the bar, you have all zeros, right? Put the matrix into REF. Yeah, so that's the one. Put the matrix into REF. So can I just show you the rest of the solution from here? I put the matrix into REF. So you see that's 3i minus a, right? I told you 3i minus a. I told you v. I just used x by z for the unknown vector. Okay, and then you put the matrix into REF. You can see that. Okay, that's the REF, the final form. From the final form, we can get the solution, right? You see the second column is the column without leading one. So you set x2 in this particular case to be a parameter r. And then you solve this equation you solve for x1. And x3, you have no other choices. x3 has to be 0. I'm trying to say the solution set is x2 is r, x1 is r, right? x3 is equal to 0, right? Using the values of x1, x2, x3 as the components, and then you let r run through all the real numbers, so you have e sub 3. Again, e sub 3 is the eigenspace for the eigenvalue of 3.